You've heard of Occam's razor, right? Of course you have. It's one of those famous mental tools we all think we know, a go-to for solving complex problems. But what if the version we all know and love is actually kind of blunt? Well, today, we're going to sharpen our understanding.
So this is the one we've all heard a million times, and it just feels right, doesn't it? When you hear hoofbeats, you think horses, not zebras. Don't overcomplicate it. It's that satisfying common sense rule that the simplest explanation is probably the right one.
And here's where things get really interesting. That popular, bite-sized version, it's not just a little bit off. It misses the entire reason the razor is so powerful and precise. In fact, that simple idea that simple is best can actually lead you down the wrong path. So let's get to the real story.
All right, to really get this, we've got to go back in time to the man himself, William of Ockham. But here's a cool little fact. He didn't actually invent the idea. He just became its biggest champion. Turns out, the concept is way, way older than you think.
I mean, we're talking ancient Greece here. Aristotle was already thinking along these lines centuries before the Common Era. Then, fast forward to the 14th century, and that's when the English friar William of Ockham enters the scene and makes the idea famous. And it doesn't stop there. Even the great Isaac Newton baked his own version of it right into his groundbreaking rules for doing science.
And here is where you can see the difference clear as day. The popular version is just vague, the simplest explanation. What does that even mean? But Occam's original principle is so much more precise. It's a strict rule. Entities must not be multiplied beyond necessity. It's not about simplicity, it's about not adding extra stuff.
And that phrase, beyond necessity, that is everything. The key takeaway here is that the razor isn't telling us to pick the theory that's the prettiest or the easiest to understand. No, it's a rule about efficiency. It's telling us not to invent extra baggage, extra causes, extra forces, extra unproven assumptions, unless we absolutely need them to explain what we're seeing. Don't make things needlessly complex.
So why is this principle so powerful? Well, it turns out it's not just some dusty old philosophical preference. We've now discovered that the razor is actually baked right into the rigorous logic of probability theory. And that, well, that changes everything. Yep, today's cognitive scientists and statisticians have something they call the Bayesian Occam's razor. It shows, using cold, hard math, exactly why we should be skeptical of theories that are too complicated. And the whole thing boils down to one single concept: flexibility. A complex theory, one with a ton of moving parts and extra assumptions, is what we'd call highly flexible. You can twist all its little knobs and dials to make it fit almost any data you find. Now, that might sound like a good thing, like the theory is really powerful, but it's actually a huge weakness. A theory that explains everything really predicts nothing at all. Think of it like this. A detective has a simple theory. One person committed the crime. Now, that's a risky theory. It makes very specific predictions. If the evidence doesn't match, boom, the theory is toast. But what about the complex theory? A giant conspiracy involving 83 people. That is incredibly flexible. No matter what the evidence is, you can just adjust the story, right? Oh, that person was the lookout, this one created a distraction. It can be twisted to fit anything, which makes it nearly impossible to prove wrong, and, as it turns out, much less probable. Okay, so the math that really powers this idea is called Bayes' theorem. Now, don't worry, we're not going to get lost in the formulas here, but the core idea is pretty simple. It's just a way for us to update how strongly we believe in a hypothesis, like our simple model S, once we see some new evidence E. And then you do the exact same calculation, but for your big, complex model C. The equations look pretty similar, but the real magic happens when we actually compare them. Here's why the simpler theory wins. Because it's less flexible, it basically stuck its neck out. It made a very specific, very risky prediction, compatible with only a tiny slice of all possible outcomes. So when the evidence actually lands in that tiny slice, whoa, the simple theory gets this massive boost in credibility. The complex theory, well, it could have explained that outcome and 1,000 others, so it gets way less credit. In the world of probability, it pays to be brave. All right, enough theory. Let's see how this razor works in the real world. And we're going big. Let's apply it to one of the single greatest mysteries in all of science: dark matter. This is the perfect cosmic detective story for our newly sharpened tool. So here's the case file. Astronomers have figured out that a shocking 85% of all the matter in the universe is, well, missing.
We just can't see it. But we know it's there because of 3 key clues. 1. Galaxies are spinning so fast at their edges they should fly apart, but some invisible something is holding them together. 2. Gravity is bending light from distant stars way more than it should be. And 3. A key signal from the early universe is colder than our theories say it should be. So you have dozens of theories trying to explain this. How do you sort through them? You apply the Q-tracer. Let's just look at 3 theories that try to solve this without inventing new exotic particles. Dur's theory? It explains the galaxy rotation, but that's it. Yehelom's theory? A little better. It explains 2 out of the 3 anomalies. But then there's this one theory from Eugene Ox. And get this, it manages to explain all 3 pieces of evidence without inventing any new particles or changing the fundamental laws of physics. It's a perfect example of the razor at work. He didn't multiply entities beyond necessity. And according to a proper application of the razor, that makes his theory a prime suspect. But, and this is a really, really important but, Occam's razor is a tool. It is not an infallible law of the universe. And there are some areas where applying it blindly can actually be a very dangerous thing to do. Just listen to this warning from Francis Crick. Yep, the guy who co-discovered the structure of DNA. He was spot on. While the razor works beautifully in a field like physics, which is often searching for simple, elegant laws, biology is a completely different beast. And why is that? Because of evolution. Evolution isn't a neat and tidy engineer. It's a messy tinkerer. It works with whatever parts are just lying around, building complex, clunky solutions on top of what was already there. The most elegant or simple mechanism isn't always the one that helps an organism survive. And you know, history is littered with examples where the simpler idea turned out to be wrong. There was a time when postulating tiny, invisible atoms was seen as a needlessly complex idea. The simple theory was that matter was just continuous. Sometimes the truth really is more complicated than we first imagined.
So let's bring this all together. We've taken that dull cliché that everyone knows, and we've honed it into a much sharper, much more precise, and frankly, much more powerful tool for thinking.
We started with that bumper sticker slogan, the simplest theory is best. Then we refined it to what Occam actually said, don't add stuff you don't need. And finally, we sharpened it with modern science to get to the real powerhouse version, prefer theories that make fewer unproven assumptions and are less flexible, the ones that take the bigger risks.
And this isn't just for scientists. This is a tool for all of us. It's a way to cut through the noise, to challenge our own biases, and to demand better evidence for what we believe. So I'll leave you with this question. Now that you have a much sharper razor, what unnecessary assumptions can you finally shave away from your own thinking?